Today's lesson is going to pick up with a conversation about chemical and physical properties and chemical and physical changes. This is the third section in our chapter 1. Let's look at this important vocabulary word that I'm showing us together. It's called a physical property. We're going to define that as a characteristic of matter that's not associated with a change in its chemical composition. Things such as density, color, hardness, melting points and boiling points, and electrical conductivity are all examples of physical properties. I think of this term property as an adjective. What can I say about a substance without changing its identity? I can tell you that water has a density of 1.00 gram per mil. I'm telling you about water without changing its chemical composition. I can tell you that an ice cube will melt at 0 degrees Celsius and that a pan of water will boil at 100 degrees Celsius. I can tell you that copper is a great electrical conductor, copper wire, for instance. I'm giving you descriptions or qualities of matter, but I've not changed its identity. With a physical change, I think of this word as a verb, an action word, the process of changing perhaps its shape, its state of matter, but without changing any accompanying chemical composition. For example, a physical change. If a solid melts to a liquid, melting. If I take a solid and put it into water and create a solution of salt, for instance, creating sodium chloride in water is dissolving. I've not changed the identity because I can evaporate the water away and get the solid salt back. That's a spelling error. Grinding and evaporation. Evaporation is a liquid going to a gas. So any phase change is an example of a physical change. Any process of dissolving or simply changing shape are also examples of physical changes. It is an action word, but it does not result in a new compound. Now, on the opposite side of that coin, we have the term chemical property and chemical change. And again, when I think of the term property, I think about the adjective, a quality that I can use to describe a substance as it's undergoing a change. And the verb is the actual chemical change. So a description of the ability to change one type of matter into another type of matter. For example, flammability, toxicity, acidity, reactivity, heats of combustion, oxidation. These are all adjectives I can use to describe matter as its ability to change into a different kind of matter. The process of undergoing that change is a verb. So, for example, when a metal reacts with an acid, when a metal rusts or oxidizes, the combustion of different fuels, digesting your food, cooking an egg rotting, these are all examples of chemical changes. You made something new. I suggest you pause the video here and just challenge yourself. This is a homework question from Sapling. How would you label each of these changes? Is it chemical? Did you make something new? Or is it physical? You did not make something new. Chemical or physical? These all relate to the metal lithium. You try it and then start up the video when ready. Silvery gray in color. I'm describing color as a physical quality. Changes from silvery gray to black when placed in moist air. Well, lithium will oxidize in air. It will tarnish. It's in the liquid state as it boils at 1317 Celsius degrees. I'm telling you about a boiling point, a physical quality. It can be cut with a sharp knife. Here I'm seeing a key word, reacts. Reacts with is a chemical quality. It's in a liquid state, reacting spontaneously with its glass container. Reacting, chemical. burns in oxygen, chemical. And light enough to float on water, well, that's a physical quality called density. I hope that was comfortable for you. Let's look at another example. Here's kind of a molecular model where we're asked to just decide, is this chemical or physical? Let's start up here just as a common point to look at the top of the flow chart. I notice that I have a molecule consisting of 2 blue atoms and another molecule consisting of 2 red atoms, kind of bonded together to make a diatomic molecule. I'm going to write that word, diatomic. 2 atoms bonded together. I'm sorry, excuse me. When we process from circle 1 to circle 2, kind of heading down the row here, we notice that all of a sudden, looking from here to the next circle, I have a different type of molecule. Oh, it's still diatomic, but now I have a blue and a red atom bonded together. That's new, isn't it? It wasn't in the original. Making something new is a chemical change. If I continue going down, I have a combination of red to blue atoms. I still have a couple of blue to blue atoms bonded to make a diatomic molecule. But now as I look down in circle 3, I have something completely new. I have a whole different arrangement of chemical bonds. This particular molecule is made up of 2 blue and 1 red atom chemically bonded together. That's something new, therefore a chemical change. Let's move from circle 2 to what I'll call circle 4. And I know that these are divided into 2 halves. So remember over here how we had molecular blue to blue atoms. They've been physically separated into a separate container, but they have not changed. And right here, I see that I still have the blue to red atoms bonded together. They've been physically separated into their own container, yet they have not changed. Physically separating a mixture is a physical change. Let's talk about from what I called circle 4 down below here. This looks like a highly disorganized system, and when I look down here, it's now become quite organized. This looks like a phase change, creating a solid from perhaps a gas. And I'm saying gas because those molecules don't look organized at all. A physical change is we create a phase change. Even if it were a liquid and we solidified, it's still a physical change. Let's go to the top now. These blue diatomic molecules have been separated. Remember, to separate a molecule that's bonded together, you break bonds. You can't physically separate them. You must chemically break a bond. That's a chemical change. I'm sorry, I'm coughing. All right, so let's continue there and see what's next. Let's talk about intensive and extensive properties and 2 important vocabulary words. Intensive refers to the property of matter that does not depend upon the amount of sample you have, independent of size. Intensive, independent of amount. Extensive, it does depend upon the amount of the sample present. Let me give you some examples to bring meaning to these terms. Intensive properties are independent of the amount of sample you have. I can tell you that water has a density of 1.00 grams per mil. I don't care if it's in a cup of water or a gallon of water or a lake of water. As long as it's pure water, 1.00, it's independent of the amount of matter. Boiling points, color, and temperature are all independent intensive properties. Extensive deals with extensive properties do depend upon the amount of matter. If I have more matter, it will have more mass. If I have more matter, the volume will be greater. If I have more matter, it will contain more energy. Dependent upon the amount is the extensive properties. So here, let's try some examples from our homework. We defined intensive as independent of the amount of quantity you have, and extensive does depend upon the amount of sample you have. The boiling point is a constant number. The ratio of mass to volume is called density. It is an independent number. The temperature of a substance will read the same regardless of how much you have, as will the color. The mass does indeed depend upon how much you have, as does the volume and the length. But hardness is a quality of a substance independent of its amount. Intensive and extensive are two vocabulary words we should become familiar with. Of course, we weren't in class today, so I'm skipping through that. And we're going to talk a little bit now in Lesson 4 about units of measurement. We need to identify the SI. That stands for Standard International Units. In other words, everyone but here in America. Standard International Units, the metric system. In terms for length, mass, volume, density, temperature, and time. What is the base unit for each of those measurements? And we'll start practicing by performing calculations that convert in the metric system from one unit system to the other, becoming familiar with the prefixes used in the metric system to represent the magnitude of 10. Here's a chart that I'd like to look at with you very carefully. We have in the first column the measured amount of substance. What property are we being measured? Length, mass, time, temperature. These are all measurable properties. The name of the unit is the base unit that will measure that property in, and then we'll see the symbol in column 3. Work to memorize the base units for each of these measured properties. The base unit for length is the meter, abbreviated as a small m. The base unit for a mass is a kilogram, abbreviated kg. That's a common mistake. Notice it's not a gram, but it's a kilogram. Time is in a second. Temperature is in the Kelvin unit. The Kelvin unit, sometimes called the absolute scale, we know to convert from Celsius to Kelvin by adding 273.15 to the Celsius temperature. If you're unfamiliar with Kelvin, we'll be using Kelvin, especially in our gas laws chapter a little bit later on in the term. It's called the absolute scale, meaning that there is no zero or there's no negative numbers. Absolute zero is the total absence of kinetic energy. Time in seconds, Kelvin, and we won't really be using luminous intensity or electric current in chemistry, but by far the central calculation of a chemist is the word mole, the amount of a substance, and it's abbreviated as MOL. And you're looking at an opportunity really in that next sapling question to just practice the abbreviations. The mass we said was in a kilogram, the length was in a meter, the time was in a second, and the temperature is the Kelvin scale. It's an opportunity to make us remember, which we're working to memorize, the standard international unit as the base unit for each of these measurements. We also want to work to memorize the metric prefixes, work to remember these. Although I'll tell you that there's a test-taking tool page that you can create from watching one of the Canvas lessons on the metric staircase. I highly recommend making that. It's worth listening to that video in your Canvas lesson in section 4 of chapter 1 and make that staircase, and you can use that on your test. Here are the list of prefixes and the magnitude of 10 that they represent. Some of them might be more familiar to us than others. For example, I bet you heard of milli as 10 to the negative 3, centi to the hundredths, deci to the tenths. Kilo is 1,000, mega is 1,000,000, giga is 1,000,000,000. Some of them may be more familiar than others. Our job is to become comfortable with those and recognize the magnitude of 10 the prefix represents. If you were to look at a prefix list, such as this on your homework page, always know that you can look them up if you make your own test-taking tool page from the Canvas lesson or work to memorize. You would remember nano is a negative 9th power. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 1 nanometer. Kilo is a positive. It is 1, 2, 3 magnitude of 1,000. Centi is to the hundredths place, 10 to the negative 2. Micro is a millionth, 10 to the negative 6. Milli, 10 to the negative 3. And mega, million, 10 to the positive 6. How are you doing with those? Do you know those by heart? Sometimes we have derived units. In other words, we can take those base units we're working on remembering and start creating derived units from them. From those 7 standard international base units, we can derive other units of length to define a unit of volume, and the base unit of mass and length to define a unit of density. Let's talk about that. Here's a cube, and it looks like a cube we know has all sides are equal. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares in any direction. They're all the same no matter which way we go, a cube. Let's suppose this entire blue is a meter in length and in height and in width, 1 meter cubed. If we were to pull out 1/10, notice how those were tens as I counted across, pull out 1 cube that's 1/10 the size of the original cube, 1/10 is a deci, isn't it? Deci is 1/10. I would have 1 decimeter in length, in width, and in height, a decimeter cubed. In terms of a volume, that's equivalent to 1 liter. This cube, 1 decimeter on each side, would hold a volume of 1 liter of water if you were to pour it inside that cube. Imagine doing the same thing again, dividing this decimeter equally into 10 specific cubes. So you have a cube, I can't draw that well, but you have a cube that's 1 centimeter by length, by width, and by height. So you have a centimeter cubed. That would hold a volume of exactly 1 milliliter of water. We need to know those conversions, that a cubic decimeter holds a volume of 1 liter. That allows me to change from a length measurement to a volume measurement. And I want you to know that 1 cubic centimeter is equivalent to 1 milliliter. This cube that we made from 1 centimeter, 1 decimeter, 1 meter, remember it's cubed because all sides are the same length, that cube would hold exactly 1 milliliter of water. And in terms of density, we have a derived unit that compares a ratio of a substance's mass per unit volume. If we measure mass, let's say in a gram, and a volume, let's just say in a milliliter, the density has a derived unit of a gram per mil. And in this slide, we get an opportunity to actually practice our very first density problem, knowing that density will be the topic of your first lab. We asked for the density of lead if a cube of lead has an edge that's 2 centimeters long and a mass of 90.7 grams. Density is defined as the ratio of mass per unit volume. I'm going to show you what I call a round little buddy, which is just an algebra tool that helps us find the formula for any of these variables. So I'm going to place density over mass over density over volume. I spelled that wrong. And I'm going to read that story problem again. I have a cube of lead. All sides are the same length in a cube. By definition, if it has a width of 2 centimeters, it has a length of 2 centimeters and a height of 2 centimeters. The volume of this regularly shaped object is length times width times height, 2 cubed. Since the unit is a centimeter, we multiply the length of 2 centimeters by the width of 2 centimeters by the height of 2 centimeters. We get a unit that's also derived as a centimeter cubed. So the volume that we've just solved for is 8 cubic centimeters. The mass that we were given was 90.7 grams. We want to know the density. See what I'm doing with my algebra? I'm placing the number into this round little buddy for the given quantity it's giving. So mass, 90.7, volume, 8 cubic centimeters, and I want the density. If I want the density, I compare where these numbers lie. See how they're on top of each other? Mass over volume means to divide. So I'm going to take the 90.7 on my calculator, and I'll divide it by 8 cubic centimeters, and I'll get an answer. 90.7 divided by 8 equal. And my calculator says 11.3375. Let's look at our sig figs, and I see that there's 3 sig figs in each of these answers, so I know that my answer can have 3 sig figs. 11.3 grams per cubic centimeter. Good work. And this is a slide that shows us that process. So we found the volume first, length times width times height, and we solved for the ratio of the density, mass over volume. Let's try some from your homework so you become confident in using what I call the round little buddy of density. Mass over volume is defined as density. I like to use that to fill in the quantities as we find them. The density of ethanol, which is a common laboratory solvent, has a value of 0.789 gram per mil. What is the mass in grams if it has a volume of 133 milliliters? This is what I want. I want the mass. So where are the numbers? Well, the numbers for D and V are right next to each other. And if they're right next to each other, we know to multiply 0.789 grams per mil times 133 mils cancels our unit, and we'll need to multiply to get a correct answer. Sorry about Daisy and Dash back there. Someone walked by the window. 0.789 times 133, and my screen reads 104.937. We're allowed 3 sig figs, so I'll place that as 105 grams. Acetone is a common solvent, and it has a density of 30 grams. This looks very familiar. All right, so we're going to try that round little buddy again. M over V is defined as density, mass over volume. The density is 0.7899 grams per mil. What is the volume if I have 30 grams as the mass? Well, this is what we want this time. So I can see the math places 30 over the density. The gram units would then cancel, and you're left with milliliters as an answer. So 30 over 0.7899. I'm just doing that twice to be sure I hit it right. 39.979. We're allowed we're allowed 3 significant digits. This looks like it would need to round up 40 mils. Notice how I made 3 sig figs in my final answer. So just to kind of highlight, your lab that's upcoming, your very first experience will have 2 lab components. Part 1, finding the density of an irregularly shaped object using water displacement. And part 2 is finding the density based on a regularly shaped object. When I said water displacement, you're going to use a graduated cylinder to find the volume of water displaced when I place an irregularly shaped object inside of the cylinder. And you'll use an electronic scale to measure the mass. So let's say we need to run 3 trials, and I'm just going to talk you through what's going to happen. You're going to walk to the scale, and you're going to weigh out a certain amount of an unknown metal that has no regular shape. They're just like little granules. You could not take a ruler and measure a length times width times height. So a scale will get you grams. May I make up a number? I'm just going to say you weighed out 2 grams just to have a number. Then in a graduated cylinder, you'll have some water in here. And let's just for purpose say it's at 20 mils. You'll take this metal and you'll plunk it in. And instead of reading 20, now let's say it's reading 30 because you have chunks of metal in there. If you started at 20 with no metal and you ended at 30 with the metal, you displaced 10 mils of water. That means the volume of that particular mass was 10 milliliters. All right, that's trial 1. You gathered a mass, you gathered a volume. Now in trial 2, do not take the metal out. Leave it there. Let's say you go to the scale and I want you to add more metal into it. I want you to add 2.5 grams. I'm making these up. You'll have to read your directions. But let's say you add 2.5 grams more metal. Into this graduated cylinder, you're adding 2.5 more grams. That's your second trial. So what's the total mass in there now? Well, you started with 2. You added 2.5 more. So the total mass is now 4.5 grams for trial 2. Let's say now, after I added the 2 grams, it went up again. The water level was at 30. Let's say it went up to like, I'll say 42. Just making it up. If the total mass is 4.5 grams, remember your original volume started at 20, and now it's at 42. You displaced a new volume of 22 milliliters. There's your ratio for your second point, mass over volume. Let's say you add even more in the third trial, 3 grams. Now what's the total amount? Remember, never empty the cylinder, just keep going. From trial 1, you added 2 grams. Trial 2 was 2.5. Now you added 3 more. Inside that cylinder is 7.5 grams for trial 3. And when you added more, the water got displaced even higher. So let's say now it's up here at, 48. The total amount was back to the beginning. If it started at 20 and is now at 48, it moved 28 mils. So I want you to use the additive property to find trial 1, trial 2, trial 3. What you'll end up doing is plotting your mass over volume relationship. Trial 1, smallest mass, smallest volume. Trial 2, a little bit bigger mass and a bigger volume displacement. Trial 3 was the heaviest, therefore the greatest amount of volume displaced in the cylinder, and you'll plot that straight line, the linear relationship of density. You can see the slope of the line is always the same number. It is an intensive property. So the slope equals the density, rise over run. You'll talk about more in the lab. Here's a better picture. This is a better picture of what I was drawing. It's called water displacement. Now, here's the first graduated cylinder with just some water in it, and it's telling us it's reading 13.5 mL. Then I place this rebar, this object of an irregular shape, so I'm finding its volume through water displacement. I plunk that piece of metal into the graduated cylinder, and I see that the water level rose to 22.4. The final volume of 22.4 mils, the initial volume of 13.5 mils, creates a difference of, better hit my calculator, 22.4, subtract the 13.5, and it moved by 8.9 milliliters. There's the volume of your metal rebar. Density is a ratio of mass per unit volume. This particular problem gave us a density that we were looking for, so this is what we want. 8.9 milliliters was the water displaced, therefore the volume of your sample, and the mass was given as 69.658 grams. You can see the relationship of M over V, so we know to divide. I'll hit that for us. 69.658 divide by 8.9. My calculator reads 7.8267 and even more decimals after that. How many are we limited to? We're limited to 2 sig figs, the volume unit. So when I look at this number, I can round to 2 sig figs. 7.8 grams per milliliter is my derived unit for density. More practice coming in the lab. So just to remind you, you have a lab book requirement I'd like you to read through in your Canvas session. You have things that must be accomplished prior to arriving, along with your safety module. That should be finished up here pretty soon. And we'll talk a little bit more about this next time I see you in class, of how to create an A+ lab report. And that ends the topic of this video. The next video will contain lessons for 5 and 6. Oh my God.